Welcome. My name is Wamozo Cosmas. I'm going to take you through a review of the study of interpretation methods for future interpretable machine learning. I'm going to take you through the introduction, the necessities of interpretable machine learning, the research gap, the interpretable methods with the self-explanatory model, and interpretable methods with the self-explanatory model with specific scheme, and then interpretable methods with the co-explanation model, and then the conclusion. Most of the current machine learning techniques, despite the high accuracy, are black box models. All we know is the prediction, but we don't know how they arrived at that prediction. A correct prediction is usually the partially solve the problem at hand, but we need to know how the model makes the prediction. Interpretable machine learning assists us to solve that problem and gives us evidence for the black box model application. So despite various interpretable machine learning methods, the perspective and meaning of the interpretations are different. So this study comes in to classify to categorize existing interpretable methods, and it divides them into two categories. There is the self-explanatory model and interpretable methods with external co-explanation. Why do we need interpretable machine learning? One, to harmonize contradictions or inconsistencies among elements of our knowledge structure in a way that outputs of machine learning models, like the predictions must match the expected. For example, if in the medical fields, they must match with align with that of the medical personnel. Interpretability is essential for some newly emerging fields like autonomous vehicles and medical AI, which are highly sensitive, where certain predictions may lead to severe loss of lives. Hence, they must be audited and explained. We have to make the model more credible. One needs to know why the model outputs a certain result in practice, especially in high-stake fields. The research gap, existing studies categorize interpretable methods into intrinsic interpretable model and the post hoc explanation, which consider the classification in terms of the time it takes us to obtain the explanation, but they ignore the characteristics of the model that constructs the explanation. So based on that, this study aims to classify to categorize interpretable methods based on the characteristics of the model, the inner workings of the model at hand, and how it relates to the data set. So the study came up with two classes, that's the self-explanatory model and the interpretable methods with external co-explanation. Self-explanatory model, of the word itself, self-explanatory, it exploits existing explainable models, both in the local and the global scope. When I say existing explainable models, I think we know the obvious ones like linear models, which are good at modeling variables with a continuous pattern, more of variables with a linear relationship, which can be described in terms of a linear function like y is equal to mx plus c. And then, but such linear models don't perform well when it comes to nonlinear data. That's why we need decision trees which are more suitable when it comes to classification. Then we have interpretable methods with external co-explanation, which is another category, which interpret the black box model in a specific way. Specificity is mainly embodied in exploring the explainable meaning of the black box model using specific methods. As we can see, one of those methods is the knowledge graph, and then you have the sharply additive explanation. Interpretable methods with external co-explanation can be divided into 3 dimensions. One, interpretation of the black box model with data examples, where we shall use an influential instance in the data set to explain the output. Then we have interpretation of the black box model with a specific method, where we can use sharp or KG, as we are going to, as I've already explained. Then the interpretation of the black box model itself, here we look at deep learning and clustering models, where they can be explained in terms of the models themselves. We have a knowledge graph, which is a way of representing semantic information between two entities. We have an entity like Mona Lisa and Da Vinci, and which share a connection, and that connection is Da Vinci painted Mona Lisa. And we have an entity, museum, which shares a connection with Mona Lisa, which is an image, which is so Mona Lisa. The connection between Mona Lisa and the museum is that Mona Lisa is in the museum. So such semantic representations are similar to how we humans understand. We usually map connections, and like I know a calculator, the relationship between me and the calculator, I use it for calculating. So such semantic representations are easy for extracting interpretable meanings. And then we have the sharply additive explanation, which is based off game theory, where we measure each player's contribution to the game. So a Shapley value is the average marginal contribution of an instance of a feature among all possible correlations. So this is a game theoretic approach to explain the output of any machine learning model. As you can see, you just apply Sharp to the output and you get the explanation, whereby Sharp comes up with an optimal value assigned to each output, which can be used to interpret a prediction made by the model. Here we are going now to dive deeper in each of the categories, beginning with the self-explanatory model and scheme-specific methods. Yeah, an easier way to achieve interpretability is to use explainable models. Like we already said, you can have we already have existing explainable models like linear regression and decision trees / rules, where linear models are good for linear data and decision trees are good for nonlinear data. Then we have specific interpretable methods like the example-based explanation, where we select particular instances from the data set to account for the behavior of the black box model. We have the sharp methods. These are methods that depend on the sharp additive explanations. Then we have those that use the knowledge graph. And then for deep learning models, those ones can be explained in terms of themselves. Like you can explore interpretable meanings from the model itself. And then we have clustering model. In the clustering model, we can use the distances between clusters. Clusters are far apart. We know that the clusters are heavily unrelated, and those that are close are quite similar, or they share certain they are more highly related. Then we have interpretable methods with the self-explanatory model, whereby this can be described in terms of the scope. Those that exist in the global scope, whereby you can entirely interpret the model, or you can only provide explanations for individual predictions. We begin with linear-based models that exist in the global perspective, where we have the GLM, the generalized linear model, and then we have the general additive model, and then the sparse additive model. But all of these can't perform well. Like say the problem with linear-based interpretable models, they can't perform well on nonlinear data. And then we have those in the local perspective where we have LIME, which is a mode agnostic, which is which was presented to explain individual predictions of black box machine learning models. Like I say, these ones only explain individual prediction, not like the global ones, which can literally give you an explanations for the entire model. And then we have the lemma. LIME makes a certain a future dependency assumption, which lemma builds upon, which it intends to clarify. So lemma is built on top of LIME with the intention of dealing with the problem of future dependence suffered by LIME. And then we go to the second category in self-explanatory, which is decision trees. These are meant to solve classification problems, and they are good at models that deal with nonlinear data. And some of the methods in interpreting these models, we have the classification based on predictive association rules, the CPAR, which combines advantages of both traditional rule-based classification and associative classification. And then we have all Bayesian frameworks. They are also classified under the decision trees or rule-based. Then for the global perspective, under decision trees, we have the TreePan, which extracts comprehensive symbolic representation by generating a decision tree to imitate the concept of a given network, and then RefNE, which improves the comprehension of trained neural networks. For the local perspective in decision trees, we have anchors, which builds on the deficiency of line, and then we have the partition-aware local model PALM, which disposes the misprediction deep neural networks. Now we go to the second category, which is interpretable methods with external co-explanation. These ones not only depend on the structure of the input, but also specific methods like the sharply additive explanations and the knowledge graphs. We can describe them in terms of 5 categories. One of the categories we can get explanations based on instance. Like I said, you have to look out for influential instances in the data set, which can be used to provide summaries for certain features. Part of the method here which exists under this variant of external co-explanation is the maximum mean disparity critique, MMD, which uses prototypes and criticism. A prototype is just an instance that represents all the data. You just have to use a certain portion of the data, and the criticism in that to come up with explanations. And then we have explanations based on SHARP. Like we already said, SHARP is just based on game theory, and it's just where you use a measure of each player's contribution to the game, and that's called a Shapley value, which is the average marginal contribution of an instance of a feature among all possible correlations. So methods under Sharp, we have the Kano Sharp, which is a Kano-based estimation approach for Shapley values inspired by the surrogate models. And then we have the Tree Sharp, which solves the problem. The problem which is experienced by Sharp of ignoring future dependence. Tree Sharp solves it by explicitly modeling the expected conditional dependence. And then we have explanations based on the knowledge graph. like I already said, the knowledge graph is just a way of representing semantic information between entities, two entities, or three or more. So these characteristics, there are several characteristics we can use as an application of the knowledge graph. We have the statistical relation learning, the recommendation system, and transfer learning. The statistical recommendation learning, these are usually high, like highly evident in statistical research, where knowledge graph is often used as an inference technique where you infer knowledge. This type of statistical relation learning includes latent future models and then the observable future models, where observable future models are more interpretable. And then we have recommendation system. These exist usually in I think most of us have interacted with them in the movie streaming aspect, whereby if you watch a movie, they recommend some for you. They use knowledge graphs whereby if a certain user or a certain entity has ever watched a certain movie which you're going to watch, they usually use the knowledge of what the other user watched next after watching that movie. More of then they recommend it to you, who is going to, where they use a reference, like if the other user watched this movie and then he watched this one, they use that reference on a new user. So knowledge graphs help us to improve interpretability based on the semantic correlation of data. There must be a correlation, like me watching this movie and then watching this one, then that correlation can be used on a certain user who follows the same pattern. Then in the field of transfer learning, there are two frameworks that where KG can provide human understandable transfer learning explanation. The first one is the portability, where knowledge graphs explain the portability of features learned by the convolutional network from one domain to another through pre-training and fine-tuning. Then the second one, where knowledge graph justify the rationality of the target domain model predicted by multiple source domains. Then deep learning methods tend to be high, to have a lot of nested neurons, which make interpretability a weakness. So it's difficult to comprehend the internal logic of the network. So we have the authors had to divide the techniques into feature visualization, network transparency, attribute tags, and autoencoder. So for feature visualization, it's usually defined in terms of convolution layer visualization and the visual characteristics of the results. For convolution layer visualization, mainly expresses the features visually acquired by the neural networks, which mainly aim at bugging the network models. Then for visual characteristics of the results, they show the basis of the judgment result and help people to understand the decision of the model. For the network disparity, here we take a deeper look at the neural networks and the methods that were classified under this subcategory. We have the singular vector canonical correlation, the SVCCA, and then we have the agglomerative contextual decomposition. Attribute tags more of utilize predictive tags and semantic annotations to generate human-friendly explanations. Usually, it's easy for humans to understand something where a tag is attached to it. So this is an easier method to develop and promote in practice. And then we have the autoencoder. The autoencoder is a kind of artificial neural network used in semi-supervised and unsupervised learning. Its function is to perform representation learning on input information by taking the input information as the learning target. It's usually combined with sequential data. So, and one of the best uses for autoencoders is they are usually used to improve performance of interpretable methods. But their limitation is that they rely on existing interpretable methods to have a better interpretation effect. And then we have explanation methods based on clustering model here. Like we already said, for clustering, you can use the distance between the classes or the clusters as an interpretation method. And you can use tools like scatter plots to explicitly provide information about the clustering features through the relative position of objects on the scatter plot. So here we have just a high level structure of everything I've talked about, where you have interpretable machine learning methods, and then you divide them into those with self-explanatory mode and then those with the external co-explanation. These can be classified in terms of linear and then decision tree, and you can classify them even based on scope, where there are some that work well under the global perspective, and then those that work well under the local, and they're listed there. Then for co-explanation, you can use influential instances in the data set to come up with explanations, and then there are those that can leverage the sharply additive explanation. We have Kano sharp and the tree sharp. This is just a high level definition of everything. And then for conclusion, we have seen that the authors successfully categorize the interpretable methods under two categories: self-explanatory model and then the interpretable methods with external co-explanation. But there's a lacking element of measuring or quantifying the measurement of interpretability. How good is the interpretation? So that's more of a pending field of research, and it might stimulate or motivate future researches in the field of interpretable learning. Thank you for listening to me. That's all I had for you for this review.